Oh, yeah. Ready? I was like, or I like
Okay, so it's 7:30 and we're going to get started. Our vice president doesn't know that we're going to start the meeting. Guys, we're going to get started on our meeting here. I'm going to come to some of your classes. I'm telling you. I'm coming. I'm going to come there and stand there and talk the whole time you're doing a class. Okay, so welcome to the December meeting of the Johnson Space Center Astronomical Society. Mel, can we start our meeting? Thank you. Okay, so welcome to the December meeting. And here is, our opening slide here is a beautiful picture from Stan, who couldn't make it tonight. The Horsehead Nebula he took actually at Fort McCavett just a couple months ago. So Stan contributed that for our opening slide. Beautiful, ugly sweater you got there, Dave. I love it. I hope you know it's ugly, right? Yeah. All right. Here's our agenda for this evening. And before we get started, I'd like to see if there's anyone new here. First time you've been here, raise your hand. Tell us your name, how you found out about the Johnson Space Center Astronomical Society, and what your interest is in astronomy. Right here.
Michael Spencer, approaching retirement, always wanted a telescope, did poking around the internet, found the club, came to learn.
Excellent. Well, welcome. We're glad you're here. Right up here.
My name is Simone Duffy. My friend Forrest told me about your group, and I've just been fascinated with astronomy all my life. Go and check it out, and I'm very glad to be here. Thanks.
Great. Wonderful. Thank you. Do you work with Forrest by any chance? No. Okay. I was going to say another JSCer, but maybe not. Okay. Anybody else? First time here? Oh, you guys.
My name is Paula Sanin. I'm from Caracas, Venezuela. It's my first time here.
Very good. Thank you. And
Egisto Garcia, we're from Venezuela. We live in Seabrook, and we like to hunt stars when we are sailing.
you like to start where you're failing?
We like to hunting stars
Oh,
when we're sailing.
where we're failing.
Stars when he's sailing.
Oh, sailing. Sorry, I said failing. Hearing. Okay, so great. Thank you. Well, welcome, Venezuela. I think that's maybe the first that we've had from Venezuela. That's wonderful. Anybody else first time here? Everybody else looks familiar to me. Okay, very good. We are going to move on. Okay, so if you'd like to get on our email distribution, there are two different distributions. One of them at the top is for meetings only. You can send something to that email address, and Ron will put you on our meetings only. And the bottom one, you'll get to David, and that is for everything. Or where Chris is, our doorman, he has a clipboard. Hold the clipboard up. And that clipboard has a bunch of tear-offs, and you can get those email addresses off the tear-off, and you can send an email to one of these and get on our email distribution so that you'll know what's going on and be able to join us on all our activities. Okay. All right. I hope that's okay. I see somebody writing out there. Okay, speakers. Uh-oh. Trevor. Where'd Trevor go? Oh, boy. Okay, Trevor is not here. He deserted us. Okay, anyway, speaker, sorry, but we don't have a pointer, it appears, tonight. We usually have a mouse pointer you can use to point at things, but Trevor is not here, so I don't know. We didn't activate it.
I have one, but
That
I don't know if it's going to work.
that has nothing to do with what I'm talking about. We have a mouse pointer on this so the online people can see the mouse pointer. Yeah, but we forgot to activate it tonight. Sorry. Okay, so there's two mics you guys need to talk into. There's this mic for the room, and there's this mic here for the computer. So as a speaker, guys, you can't really go anywhere because if you go somewhere, people online won't be able to hear you. So you pretty much got to stand in this general area to be heard. Okay. Okay, so for our main speaker tonight, we've got Justin. He's going to tell us about the nature and weirdness of globular clusters. And before Justin comes up here, I'm going to tell you just a little bit about this fella. Justin McCollum graduated from Portland State University and UT Austin with a BS and MS in physics in 2002 and 2005, and a PGP certification in AIML with the McCollum School of Business, August 2023, graduating at the top of the 2023 cohort. He's employed at Lamar University as the physics laboratory coordinator and departmental astronomy. You gonna be able to fix the pointer? Great, thank you, Trevor. Trevor's gonna save us, woohoo! Lamar University is the physics laboratory coordinator, thank you, and departmental astronomy and space sciences instructor. He also works as a part-time education instructor for the Educational Department of Space Center Houston, a longtime member of the following academic societies promoting astronomy and planetary sciences, STEM outreach with the Planetary Society and American Association for the Advancement of Sciences, plus outreach and education on weather and climate sciences with the Union of Concerned Citizens, all since 2014. Justin received honors and awards with various advanced observation programs at the Texas Star Party and the Texas Governor School through the School of Education and Special Populations with Lamar University from 2007 to 2021. He'll be joining in research, teaching, and developing courses for UHCL starting in January for the future pursuit of a PhD in astrophysics of space sciences with Dr. Samina Masood. There she is. Woo-hoo! Sorry. We just love Dr. Masood, so we always got to make a big deal when we put her name. All right, so with that, Justin, come on, tell us about globular clusters.
Leave him to make a big pizzazz over everything.
Hey, see, Justin, you fixed our pointer for us.
Yes. All right. Let's see here. Okay, so I did this talk for many different clubs, and we think of globular clusters as being just these plain balls of stars. What we know about them is that they are large concentrations. I call them islands of stars. They can either be elliptical or spherical shape. They're very old. They formed out of separate concentrations of dust and gas that broke away from the protogalactic clouds that would form the galaxies. They're very ancient stars. They have very little concentration of metals, mostly hydrogen and helium. The ancient dust clouds that formed these globular clusters occurred very early. And unlike nebulas in our own galaxy that tend to turn 10%, 30% of their dust and gas into stars, these can be over 80% efficient in terms of turning dust and gas into stars with the star formation. They're very poorly understood. There's a lot about globular clusters we do not know. And hopefully a lot of that data from the James Webb Space Telescope can tell us a little bit about the origins of globular clusters in our universe, because they can be the building blocks for galaxies just like open star clusters. There are multiple stellar populations that exist in these globular clusters, and the chemistry and the classification of the stars fit very much like the old stars we find in the galactic bulges or in the elliptical galaxies, very, very reddish in color. I'll go through this quickly. Johann Abraham Elie was the first to actually observe these globular clusters. His first observation was back in 1665. This actually appears in Charles Messier's work. Over there is from William Herschel's publications. This is a repeat of that publication in 1912 from the time of 1783 through 1785. I show a picture here of the Sagittarius, and it's in that area there where Mr. Elie was actually looking at M22 while doing observations with Saturn. Unfortunately, none of his works have survived. There's no known portraits, but Charles Messier actually referred to his works when doing the observations. I won't go much into this, but we should all be familiar with Charles Messier. He discovered 13 comets, but actually came across many more of these sort of fuzzy objects that sort of stayed in the sky in a particular constellation, didn't move around. There were a lot of contributors to the catalog. Messier probably only discovered about half of the objects he contributed to his catalog. The rest were contributed over many, many, many decades. The final catalog was published from 1921 through 1967 with the addition of 7 objects. Messier 110, I should have put that in the list, was from the discoveries by Caroline Herschel, William Herschel's wife. And here we have some of the old writings. We can actually look at the date. I believe that is the 3rd of June, 1764. And there's his writing in French from his publications from 1784, referring to Messier 15. Now, the image on the lower left is more indicative of what he would have seen in his speculum mirror, in his metal mirrors. Now, this is with William Herschel, and this comes from his observations from his 20-foot telescope. And we can see right over here, we can look at what are globular clusters, nebulas, groups of galaxies. And right here, I think that's very indicative of one of those nebulas that actually has a star at one end and it's shining outwards, like Hubble's Variable Nebula. Now, he had 2 publications in 1802 and 1820, but there's some 15,000 other non-publicated observations. Yes?
On the previous page on Messier, when he discovered M31 and M32, obviously they're numbers next to each other, so he saw them right on the same field of view when he was looking at them.
Yeah.
110, did he go back there and look at it like years later and say, oh, there's something else there?
That discovery was by Caroline Herschel. Years later, M110 is pretty faint compared to M31 and 32. You have to remember, he was looking through a small refractor. This is the bigger scope, of course, that he used, the 40-foot scope. Yeah, remember, speculum mirrors have been around since ancient times. They're mostly 1/3 tin and 2/3 copper. And this was the largest telescope for 50 years. 40-foot long telescope, 48-inch mirror. He had 2 of them. The image there on the lower right is actually what we call a daguerreotype, one of the first types of photographs made. That was back in 1839. And even though John Herschel's father had been dead for decades and he was contributing to his father's work, you can still see the A-frame. You can still see the house over here. Well, this house right here that holds the base of the telescope and its gearing mechanisms. It's right over here. You still see the ladders that he would have to climb up. The bench platform and the gearing mechanisms here are all gone. But if anybody's ever looked through, has anybody ever looked through a Herschelian telescope? Basically, you get a big daub, you have a little refractor, you stare down at it, and you just record your observations. And there are cash wheels right here because the whole thing could rotate 360 degrees. Now, what's important is that we're getting into the structure of the Milky Way. This is the great debate between Harrow Shapley and Heber Curtis. And the real issue was knowing about the globular clusters is knowing about the nature of the Milky Way galaxy. This was a great debate they had back in the Smithsonian Museum of Natural History in the 1920s, because prior to that, everyone thought that the Milky Way was the whole universe. This was about debating the properties and the features of our galaxy, whether or not there was more to the universe than just the Milky Way galaxy. It was a big debate back then. Shapley, of course, was right about the nature of the Milky Way galaxy, but he was wrong thinking that it was the only thing to the entire universe. Curtis was the complete opposite. He had an incorrect assumption about the size and structure of the Milky Way, but he thought there was more to the universe than just the Milky Way. And no one thought about elliptical galaxies existing, so when they looked at these spiral nebulae, they treated them like island universes, like this was a cosmos, and all these spiral nebulae were like separate universes. And the galaxy comes from galactica, which comes from the ancient Greek, referring to the mother Hera and the spilling of milk across the sky, that cross connection with the Latin for the Milky Way. Now, you can see the assumptions astronomers had about the Milky Way galaxy. You see there up to the upper right, that was an image by Cornelius Epstein, who really thought that our solar system was the center of the Milky Way galaxy. You can see this big bulgy of material right here along the edge, which is really the center of our galaxy right there. The first move was going from the geocentric to the heliocentric, from Earth-centered to the sun-centered solar system. Now, the real goal was moving away from our solar system being the center of the Milky Way galaxy and then being more to the universe than just the Milky Way galaxy. These were all the assumptions about our sun being at the center of our galaxy. This is William Herschel's work. Over here, this is more with Shapley's map. He had right over here that yellow dot is our own sun, and that the red X is the center of the Milky Way galaxy, and all those green little spotches right there are all globular clusters. So he had a more moderate view of the structure of the Milky Way galaxy by looking at these globular clusters. Now, how many globular clusters do we have? Well, we know about 169 of them. Some of the catalogs vary between 150 and 180. One thing I like is the Caramango catalog. This comes from an Italian astronomer who actually looked over a period of 2 years at some 1,100 objects as targets for galactic star clusters and globular clusters. At least 5 of these have been added to our list of known Milky Way globular clusters. And there's the potential to add hundreds more. And we're finding a lot of these pretty much close to the galactic bulge, particularly Caramango 1104, 1105, 1106, and 1108. You can see how we get close towards the center of the Milky Way galaxy, where the globulars have, in the amount of metals they have in proportion to the sun, the metal concentration for globular clusters get greater as you get further away from the center of the Milky Way galaxy. All right, so here we have what is certain. What do we know about globular clusters? Well, then we have the size range between 10 to 120 light years for the light radius. That deals with half the light output coming from the bulk of the stars in the globular cluster. There's what we call the tidal radius, which is the gravitational influence of the globular cluster that houses all its stars. It tends to be about 5 to 10 times the half-light radius. So when people ask you the size of a globular cluster, you can ask them, are you basing that on the light radius or on the tidal radius? Then what we have is that there are redder globular clusters that tend to have a smaller half-life radius than the globular clusters that tend to be more spread out and have bluer stars. Again, half the mass of a globular cluster resides within the half-light radius because that constitutes the bulk of the light radiating from the globular cluster. They tend to have over 100,000 stars. Most will have between 100,000 to 500,000 stars. The age range is between 8 to 12.7 billion years, but I'll show you some that appear to be very, very younger. We got 169 known for the Milky Way, but there could be a potential another 200 candidates, and maybe even more than that, to match the some 500 globulars that have been discovered with the Andromeda galaxy. Some galaxies, like Messier 87, can have over 10,000 globulars. And that's believed to be a lowball estimate. Now, let's talk about globular clusters. They fit within the population 2 stars, meaning they have a very low metallicity, meaning the amount of hydrogen and helium compared to elements even like carbon and oxygen. So the density ranges from about 0.4 to about 1,000 stars per cubic parsec. So instead of, let's say, a star as bright as Tau Ceti being 4 or 10 light years away, it can be anywhere from 1 to 1/10 of a light year away. So these stars are very clumped together, and the radiation in these globular clusters can be very intense. Now we have, anybody familiar with the Shapley-Sawyer classification system, the way you classify globular clusters? Well, it's all about the concentration of stars at the center. So you go to the upper left, then you go to the right, and you go from the top to the bottom. Basically, the concentration becomes more and more loose as you go from 1 to 4, then the next row from 5 to 8, and the bottom one from 9 to 12. So the 12, I think, is Palomar 5. You can see how that's all has no concentration whatsoever. It's all spread out. And that would be a class 12. So if you're doing the the Astronomical League's globular cluster observation program, one of the defining features is, what is its classification system? What is its Shapley-Sawyer number? Is it a 1? Is it a 3? Is it a 5? Is it a 12? Based on the concentration of the stars in the globular cluster itself, the spreading out of that light radius. Now, there's actually 2 types in terms of the chemistry. There are what we call the Osterhoff types. The type 1 is metal-rich. That is, they have a higher amount of one of these things is calcium. They tend to find in some of those more metal-rich stars. The metal-poor stars, or the type 2s, they tend to have those RR Lyrae variable stars that you can use to measure the distances of those globular clusters. Some can be the remnants of dwarf galaxies, and they tend to have a feature indicating some sort of supermassive, intermediate mass black hole at the center. There are intense gravitational tidal effects when they interact with a galaxy that can tear the stars away from it, leaving just the core. And so what you get is that you have what we call an evaporation rate for globular clusters. How many stars they lose every time they sort of circle around the Milky Way galaxy, coming in and out of the galactic plane. So there are stars that are leading ahead or behind the globular cluster because how they interact with all the big structures within the galaxy. So here's our layout. I don't know if anybody ever seen a picture of this, common in many astronomy textbooks. You've got the galactic disk, you've got the OB white stars, blue-white stars at the edge. You've got your spiral arms, the sun about 8 kiloparsecs. That's about 25,000 light years from the center of the Milky Way galaxy. It's about 90,000, about close to 100,000 light years across. But also look at the red dots on the image on the right, looking at the globular clusters, more towards the center, but more spread out throughout the galactic halo. And the orbits, they're highly elliptical orbits. They can get very close and they can get very far away. So the orbits are not only very elliptical, they're highly eccentric. So they're anything but a circular orbit. They're almost as eccentric as some of our comets. And they actually move, when you take into account the motion of all the stars in the Milky Way galaxy, you can calculate their velocities, 400 to 500 kilometers per second. So they're pretty fast, even though they take hundreds of millions of years to circle around the center of the Milky Way galaxy. What's interesting is that we can pick out the white dwarfs, and we know these globular clusters are very old because we find huge population of white dwarf stars. Some of them can be helium white dwarfs, so they're very, very basic stars in terms of their chemistry. There's what we call the main sequence turnoff point. That means we get stars in a globular cluster that can be up to the F class. No O or B or A class stars. They literally turn off from here and they end up going into this instability strip where we have the variable stars, and they end up here in these red giants. So they ship directly into this red giant branch. That RGB is indicative of globular clusters. Star formations would have occurred very early in the formation of the galaxy as these globular clusters were forming their stars. They do pass through the galactic planes when they want to do any recent star formation, like you get a bunch of white dwarfs colliding together and you get these blue stragglers. We don't see those with the elliptical galaxies, but definitely with the spiral galaxies. And when you get the giant molecular clouds like those big dark nebula and big chunks of spiral arms in a galaxy, those stellar associations. Well, the gravity as it interacts with those globular clusters are going to cause those poor little white dwarfs to collide and create those blue stragglers. And here are some of the images of those blue stragglers. Possible helium white dwarfs, so some very, very primitive white dwarfs. We get later generations of those carbon-oxygen white dwarfs. That's an image from the Hubble Space Telescope. So you can pick out those blue stragglers in there and some cataclysmic variable stars that are undergoing their own process of self-destruction. Now, this looks at two possibilities of how stars are forming in globular clusters. Those big black circles represent the very massive stars among the low mass stars. So as the massive stars explode, they lead to a second generation of star formation. So you have two generations of stars. All the big massive stars in globular clusters would have ceased because all the material from that would have formed the second generation of low mass stars. And what I have here over there on the right is how massive clusters can form from massive stars. As the massive stars die off, they create a lot of hot blue white stars, those OB stars. They end up being these superclusters. And as those stars die out and create the more older, longer living stars for the globular clusters, all globular clusters appear to have started off as these superstar clusters with those OB, those blue stars, and later form into those globular clusters. Now you get the stars that are forming together. The FG are going to be the F and G class stars. The SGs represent the supergiants. And it appears, while the physical explanations are a mystery as what is causing this progression of how the stars are forming from first to second generation, a lot of it would have occurred within the first 2 billion years of a globular cluster. And we have those blue arrows representing the radiation generated from the stars. The red arrows are the gravity holding the globular cluster together. And eventually you get some of those massive stars that swell up like that big orange circle is a big supergiant star. It explodes. And it's almost as if the first generations of stars that didn't die out are acting as sort of like a gravitational shell that's holding in those stars down here as the second generations of stars. And they're only spreading out over billions of years as they intermix with the first generations of stars. So we get our big, huge cloud of hydrogen and helium. We get the spiral galaxies that are forming. Chunks of it will break off, spinning like water shooting off from a sprinkler, and those separate lumps will form globular clusters. And as the galaxy is forming, those globular clusters are going to be attracted to the central core and will sort of orbit around that, separate from the spinning motion of the spiral arms. Now, this is very interesting. I like to show my students this. You can see how the Milky Way actually has an up bend and a down bend. It's warped from colliding with so many dwarf galaxies. But as you go towards the edge of the Milky Way galaxy, you notice how the stars are very bluish. As you head towards the center, the stars are becoming more reddish. But also look at the halo stars and the globular clusters. From the F to the G class, the stars are getting more yellowish and they're getting a cooler surface. So the globular clusters that have the hotter stars that are more whitish are going to be those at the edge of the galactic halo rather than towards the galactic bulge. So these are just, I won't go through this in detail. I mean, right here you can see the basic facts between open and globular star clusters. What's very important is that up here is the loose irregular collection of stars. Here is the dense distribution, but with open star clusters, you can have stars of any classification. But notice right here we have that spectral turnoff where the stars will only reach a certain temperature, a certain BV colored index where they can only reach a certain classification, and then they just turn off into the red. And this shows what we can find in common between the globulars and open star clusters. They're attracted by mutual gravity. They're going to have the same distance from the Earth. The stars in the cluster indicate the age of the cluster. They orbit around the center of the galaxy, and they all form from the same cloud of dust and gas. What's different is that over here are these bright blue stars, and here are these frequently containing these bright red stars. And that's very important. All these other features are important, but this is how you can really distinguish between the opens and the globulars. Now, one thing is actually measuring the distances of these globulars to map them out so we know the structure of the Milky Way galaxy. One thing is, of course, looking for what we have are the RR Lyrae stars. And here is where we have an example here with 47 Toucan. And you can see that pulse right there in terms of the times and difference in magnitude. And we can actually see those lights pulsating. This is an M3. Those are the 7 I was able to pick out. But those RR Lyrae stars, you can find them in those Osirov type 2s, the globular clusters that have very little metals in them. You can find a lot of those variable stars. There's what we call the logarithmically scaled image for RVB, which means we can distinguish by temperature and assign stars to particular colors. That way we can know more about the stars based on surface temperature and spectral, so we can actually, it's like an enhanced false coloring of a globular cluster. You can get more of a color variation. So you can see the differences in the magnitudes among those stars. And you can look at stars that are in our own Milky Way galaxy that we can use the parallax for measuring distances and know about the three-dimensional structure of those globular clusters. And here it is, where we have the enhanced, and then the image on the right is black and white, but it's a blue from a B filter, so it's a blue filtered image. And we can see the changes in the magnitude of those stars that are flickering. Those are all just, and then M3, they found some 274 known variable stars. That's one thing about the globulars versus that open star clusters. You get a lot of variable stars, particularly with the Cepheids and the RR Lyrae stars. This one here is M5, so you can see the blinkiness. This bright dot right here is going to be a Cepheid, and then the fainter ones that are flickering in fainter, greater numbers are going to be the RR Lyrae stars. This shows a difference in the RR Lyraes versus the Cepheids, and the Cepheids have that luminosity distance relationship. So as they get fainter, as they're further away, you can use these as a good indicator to measure the distances of globular clusters. And the changes in the Cepheids can also indicate the age of globular clusters. This actually is an example looking at one of the Cepheids. This is the variable star V1 in M31 in the Andromeda Galaxy. This was one of the variable stars used by Edwin Hubble to actually determine that the Andromeda Galaxy is actually a separate galaxy and not some spiral nebula that's actually a part of our own galaxy itself. It's actually part of a greater universe. Right there, you can actually see that image of the variable star V1. Now, that blue coloring right there with the color magnitude diagram is based on what we call the distance modulus. There's a difference between what the star's brightness should be if it's 32.6 light years away versus the brightness that we actually see it. And then we can relate that difference in brightness to distance. And so we can use that to measure the distances of these variable stars, and then use that to measure the distances of globular clusters and know a bit more about the globular clusters themselves. There's a bit of a timing error in this image. So V42, which is the one that's not blinking, that's the Cepheid star. The one that's blinking is an RV Tauri, which is a type of a T Tauri variable star. What's important is that both of those actually exist in this instability strip. And this is the process where we have these stars going into that turn-off, where they leave the main sequence and they head off into the giant phase over here, into those horizontal red giant branches. And we can see here the change in magnitude over the period of time and distinguish that from the Cepheids versus the T Tauri stars. And the RV Tauris are a subclass of T Tauri stars. Now, this right here allows us to look at the different methods, looking at the different types of stars, see the difference in brightness. And what we can show here is that basically the globular cluster has an age of 11.5 billion years, and it's 24,730 light years away. Why? Because the difference between this here, looking at the difference between what the star's brightness would be if they were in that standard distance of 32.6 light years, 10 parsecs, versus their current distances from our sun. And so that gives us a difference of 14.4 in magnitude. So that tells us about the distance, and with looking at the spectra, we can calculate the age of the globular cluster. Now, what's interesting about this is that globular clusters do not maintain the same orbit around the Milky Way galaxy. They can be shifted around like comets orbiting around the sun. So there can be a difference not only in the distance, which is here on the left, with respect to the center of the galaxy, but over here, it shows the difference, the fact that, well, they're undergoing a precession. The orbits of these globular clusters are wobbling around the center of the Milky Way galaxy. And they can wobble with respect to the plane of the Milky Way galaxy or perpendicular to it. So there's changes in the tilt of these orbits. There's changes in the eccentricity from being very circular to being very oblong shaped. And also the orbital periods can change over billions of years. So instead of taking 400 million years, they can take up to 800 million years with the next orbit. And the orbits are shifting. They are precessing. They are wobbling around. So it's changes over hundreds of millions to billions of years. And how do we know that? Well, we can actually look at the redshift and the velocity of these globular clusters, and we can extrapolate their orbital pattern. It's very, very tiny, but a lot of this is from models and simulations, but it's based on looking at a lot of globular clusters in other galaxies and seeing how they are moving about. And by looking at the spectra, by looking at how they move with respect to their coordinates in the sky when comparing it to our own galaxy. And so we get a change in the orbital structure of these globular clusters, which is pretty much like the orbits of comets as they change, shifting around the sun. And what we find is that we get an interesting range in orbital velocities. Usually stars that are far from the center of the globular cluster, if the globular cluster is spread out, there's a greater range in velocities. If they are tighter together, the range in velocity is a lot narrower. So it's like you have a whole bunch of cars or on the edge of Houston, they can drive around and have a range of speeds like from 50 to 100 miles an hour. But if they are closer towards downtown, they're limited like 10 or 25 miles an hour. But in this case, it's the opposite assumption because the globular clusters at the edge are moving at lower velocity. So they're going from 5 to 50 miles an hour on the edge of, let's say, on the 610 loop. But if you're in downtown, imagine you have to travel between 80 and 85 miles per hour, but you have no choice. What helps is that when they're closer towards the center, they actually pick up speed. Now, here we can actually look at the structure. We have mostly main sequence stars, and we have mostly white dwarfs towards the center of the globular cluster. So we see a difference, whereas we get further away from the center of the globular cluster, we have more main sequence stars in the middle of their lives versus the remnants of dead stars, mostly white dwarfs. And we can look at where we have lower orbital velocities versus the higher orbital velocities. But the range in orbital velocities, even though they're lower, are much greater towards the edge than towards the center. So high speed, but a narrow range in velocities. A greater range in speed, but of lower velocities for those objects out on the edge versus those at the center. And so here we get fewer stars, but there's a great degree of dispersion. So there's more dimmer stars towards the edge, but we have more stars towards the center, and they're not as dispersed. They're actually very compressed together. And so we look at the layering there. We have massive white dwarfs, brighter at the center, lower massive stars, but there's greater luminosity. And then we have very massive stars, so there's lower luminosity. So we get more and more massive stars. There's fewer of them as we get further from the center of the globular cluster, and it's not as bright. And this goes from going from the light radius to the tidal radius. This shows the changes in speed. So the faster the spin, the flatter the globular cluster. So globular clusters can be like planets like Saturn. If they spin very, very fast, they're going to flatten at the poles along its spinning axes and then bulge out along the spinning axes. And most globular clusters will spin between 3 to 8 kilometers per second. Towards the central 10 kiloparsecs, the globular clusters are actually moving around the galaxy slower than those at the edge. And those closer at the center move about in prograde orbits, while the globular clusters towards the edge are moving, in some cases, they're moving in retrograde orbits. They're moving opposite from the spinning plane of the Milky Way galaxy. I'll go through this quickly. This is just looking at the amounts of calcium in these globular clusters. And so what we find is that we tend to have higher amounts of calcium from the second class, from the second generations versus the first generations of stars. First generations of stars are mostly of helium. The second generations of stars, we see different amounts of calcium. That can help tell us about the age and the generations of stars within globular clusters. And globular clusters actually have their own magnetic fields that is affected because there are pulsars within these globular clusters, neutron stars. And they actually interfere with the galactic winds, and it actually affects their motion as they go around the Milky Way galaxy themselves. In fact, they can eject huge amounts of ionized gas that comes around them. There's in the globular cluster, in the galactic halo, they have these high velocity hydrogen clouds that become charged up as they interact with the magnetic field of these globular clusters. And it actually creates a bit of a radiation pressure that can move the globular clusters around. So it's not just gravitational. And this basically shows the globular cluster having a bow shock around its magnetic field as it plunges through the galactic winds through the magnetic field of the Milky Way galaxy. No different than you have the planets with their own bow shock, with their own magnetic fields when they're moving through the magnetic field of the sun or any planet around the home star. So the fields actually get stronger because as they move through the galactic halo, they're going to interact with those high velocity hydrogen clouds. They charge up, strengthens the magnetic field. We can actually measure the speed. So the winds, the galactic winds, moving at 200 kilometers per second. The globular cluster, just with the gravitational field, gives a 45 kilometers per second. So with 2K47, perpendicular, that is at right angles to the plane of the galaxy, moving at 245 kilometers per second. And the field can change, the field does change the rotational motion of these galaxies. So there's a magnetic effect, there's the effect of radiation pressure, and then there's also the effect of gravity. Gravity is the most predominant, but there are small changes that can accumulate, and these magnetic interactions is one of them. Okay, so let's look at some of these. This is Caldwell 79, the Vela constellation. It has probably a substantial population of black holes at its core. Male 2, which is, the G1. Has everybody ever seen the great G1 globular cluster of Andromeda, M31? That one probably has a 20,000 solar mass central black hole, an intermediate mass black hole. But it could also mean that it could also be just a population of black holes. So it could be a black hole cluster of black holes that we can find in some of these more massive globular clusters. And it's possibly a dwarf galaxy remnant. This is, most globular clusters exist very early in the age of the universe. This one right here is M87, possibly as many as 15,000 globular clusters. So we find them in many different galaxies, dwarf galaxies, all these little dots around here, all these little dots are globular clusters. And then there's the mapping of the globulars in M31. This is the Sparkler galaxy from the James Webb Space Telescope. Each one of these is the same galaxy. So we can look at the age, we can look at the red shifting. We have to remember with gravitational microlensing, I know some astronomers today were talking about Einstein's cross. And the fact is Einstein's cross is actually magnified by a factor to 10 to 100 in brightness. Looking at when a galaxy is being warped around another galaxy, it's acting as a lens. Not only the gravity is pushing the light around another galaxy, you get a foreground galaxy, in the background galaxy, the light is going around it, but also it magnifies it as a lens. So we can actually, and all these little red dots here, you see all these little red dots? Those are potentially globular clusters. So we have the potential to study the early evolution of globular clusters very early in the age of the universe. And this light has to be seen entirely in infrared because this is invisible light. All right, so this is Messier 15. I don't know if anybody's ever seen Pleiades 1. It's one of four planetary nebulas that we can find in globular clusters. This was, it's best seen in O3 filter, seeing the oxygen, in 600 power with an 18-inch mirror. I actually have it where you can actually plot it out with the star pattern. And in Stellarium, you can actually get an image of 15 and see where it's located right there. Some interesting, Caldwell 80 has a possibly a disrupted dwarf galaxy, possible intermediate mass black hole. The motion of stars spread out over 600 years in terms of observations indicates that it's an 8,200-year-old solar mass black hole at the center. It's got an M1 red subdwarf, which is Capitan star, which is probably a member of that. M104, lots of exotic stellar bodies. It's continuing its mass segregation, the separating between the two populations of stars. A lot of X-ray binaries, a lot of stars with a lot of enhanced chromospheric activity, which is unusual since these are very old stars. Some 35 millisecond pulsars, so there's some very exotic stars in this globular cluster. This one is Palomar 5. I don't know if anybody's tried to look for the Palomars. They're very faint. But this is a very severely disrupted globular cluster. It's leaving a stellar stream that's about 30,000 light years long. And it has an aspect ratio of 0.62, which means it's very flat along its rotational axes, but it's spread out. So it's a very flattened class 12 globular cluster. It's like looking at a squash football. This is Palomar 12. It actually is only 6.5 billion years old. It's the most middle rich of all the globular clusters in the Milky Way. And a lot of the stars, it's actually 30% younger than most of the stars in the Milky Way globular cluster. So it's basically a junior among the globular clusters. This one is Whiting 1. It's only 5 billion years in age. It actually has a very high metal concentration compared to its hydrogen. It's not an open star cluster, but it is an object in the galactic halo. And the way the stars are moving fits with the tidal radius of a globular cluster. There is SAGDIG, the Sagittarius dwarf elliptical galaxy, one of the 12 that's being swallowed up by the Milky Way. So there are some globular clusters in our Milky Way that are members of some of those dwarf galaxies that are being swallowed up. Messier 4, I'm sure everyone's seen Messier 4. This was the first globular cluster in which they actually discovered a exoplanet orbiting a pulsar white dwarf binary. Its orbital period is very short. There's actually a possible millisecond pulsar neutron star binary. But for such an old object, it has a high content of lithium. So it's a very lithium-rich globular cluster. And this is Mayo 2, or Andromeda's cluster. If you ever see it in a telescope, it's possibly a dwarf galaxy remnant. It's a wide distribution of multiple star generations, at least 3 or 4, which is unusual for a globular cluster. It has a luminosity of 2 million suns. So it's 2 million times brighter than the sun. Its tidal size over 500 light years. Even though we tend to measure 300 light years from here to here, there's all these stars out here that are actually influenced by that globular cluster, because we can compare the speeds of the stars closer towards the inner part of the globular cluster itself. These two stars are actually in our Milky Way galaxy as well, these two, so these are foreground objects. Caldwell 25 is the intergalactic wanderer. It's unusually rich in helium. Believe it or not, it's actually passing through our galactic halo. It came from another galaxy, and it's getting a gravitational slingshot from our own galaxy. So enjoy it while you can, because it's going to fly by through our galactic halo and travel out as a rogue globular cluster between the galaxies. So it's not becoming a permanent member. It's moving way too fast. This is Messier 71, no Lyrae stars. It has a very short horizontal branch for its HR diagram. There's no central compression of stars, so it fits the type 12. You have to look at the structure of the stars to know it's got that cutoff right there on the lower right. That's indicative of globular clusters. Otherwise, it could be mistaken for an open star cluster. And that's one thing, making sure you don't mistake a class 12 globular cluster from an open cluster, is that you got to look at that spectral turnoff right there, that bend as they go through the variable state right there into the supergiant phase and giant phase. But you can see very few stars in that instability strip. Now, this is a very bizarre one. This is either an unusual globular cluster or an extreme dwarf satellite galaxy, but it's an overdensity of unresolved blue stars. I call it the Ursa Major Blue Cluster. I found this when looking on the digital Sloan Deep Sky Survey. It's an old metal polar stellar system. It has very few RGB stars, like Artemis 4, which is defined as a globular cluster because of the way the stars are moving within its tidal radius. The half-life radius is 23 parsecs. And so it's sort of a boundary object between globular clusters and sort of the dwarf spherical, ultra-faint dwarf spherical galaxies. In fact, there's black and there's an inverted image. So you circle all the blue stars right there. And that's all in Ursa Major. This is a very bizarre one, NGC 6791, because it contains both the red and blue horizontal branch star. So it neither fits that of a globular or an open star cluster. Its dimmest stars are more than 6 billion years old. It has another group inside of it that's aged 4 billion years. It's got twice the metals of the sun. So it's possibly we've discovered a third type of star clusters. NGC 1850, I won't talk much about that, but basically we got a younger subcluster within a globular cluster that looks like it's only 50 million years old. So what we have is something that looks very, very young. There's another younger subcluster that's 4.3 million years in age. So what we have is a strange globular cluster that has side clusters to it that look very young, that have a high amount of young OB stars. So why would we call this a globular cluster? Because of the structure, the shape, the star distribution, and how they move together gravitationally, the gravity field, the tidal radius. And this is actually in the Large Magellanic Cloud. This is Westerlon 1. It's the only cluster in the constellation of Ara, but it's known for having a great variety of, there's 24 Wolf-Rayet stars, very blue stars. It's got one luminous blue variable. It's got an unusual supergiant star. All of them were formed in a single starburst formation. There's actually a very bizarre pulsar magnetar that was probably formed from a star that was 40 times the mass of the sun. So very unusual features, unusual stars, an unusual number of very large giant stars. Messier 22, one of only 4 globular clusters that has a planetary nebula. It has 2 known black holes. The only way you can see GJJC1 is you require a 20-inch aperture at 900 power. It's not very efficient in ejecting black holes, so it's possible there's a large core of a black hole cluster between 5 to 100 members. Because one thing is that they look how the stars are moving in this globular cluster, and it's indicative of possibly having a cluster of black holes. And the way the stars are moving, they're literally trapping those black holes within that cluster. Because there are some indications of the way the stars are moving on the edges of globular clusters, that there may be ejections of black holes coming from these globulars as the older generations of stars die out, the more massive ones. So no 2 globular clusters are the same. They're very weird. They have very bizarre features, and they have very strange characteristics. Particularly with NGC 6791, it has both red and blue horizontal branch stars. So it's part open cluster, part globular cluster. So it has a personality issue. Okay. And I'll just say this, one of my famous astronomy poets, "Yet may I phantom this vision deep, ere my life is rounded with a sleep." And that's it. Yes.
So you did say that they have found exoplanets around globulars, even though they're old.
Yes. Yeah, probably more like Jovian gas giants, like Jupiter gas giants.
Oh, okay.
Not rocky planets.
For sure.
Some of them will probably have less density than water. Yes.
How do they determine the orbit of cluster?
The orbital motion of the globular clusters? That's a pretty technical question, but they have to take into account the regressional velocity and the redshifting. And then look at it with respect to, there's a thing about our sun known as the local standard of rest, because our sun is actually going in an oscillating orbit as it goes around the Milky Way galaxy. So you got to correct for that, seeing if it's a nice circular orbit. and then deal with the effects of all the other motions of all the stars, and then look at the redshifting of the RR Lyrae stars in those globular clusters. Because even though they pulsate, they actually redshift. And the redshifting will change among those globular clusters. But there's also a secondary effect where it's not only how the stars are circling around the center of the globular, but how they're moving through the galaxy itself.
But there may be red shift and blue shift also, because then they are going away and then they are coming back.
Yes.
So that's the type of thing which can be expected.
Mm-hmm. But there's also a change in that as the globular clusters that are moving through the galaxy. Yeah. Any other questions? Yes.
Two questions bordering on dumb questions, but where do they come from and what are they for?
Where do they come from and where are they for? Well, some of the globulars actually came from other galaxies. Because our galaxy is a hungry galaxy, it's committing galactic cannibalism. It's swallowing up a dozen galaxies at once, and it's swallowed many galaxies in the past. But the idea is that you get this huge lump of hydrogen and helium, and as it spins to create the galaxy, bits of it break off. The less massive material, the more that's more hydrogen and helium. And those break off, and they form the globulars. And it's possible that in some of these galaxies, they created a group of dwarf galaxies, and they all just sort of merge together and end up being the building blocks for the larger galaxies. So they end up being building blocks, basically. Any other questions? Simple questions? Complex questions? Yes.
Yeah, I just want to make a comment that, those RR Lyrae stars, you can actually do this in amateur astronomy.
Yeah.
You can actually go out, I've done it myself, and go out and image these things over the period of one night and make a movie out of your pictures. You can actually see these stars changing their brightness.
And some of them you can observe them over a single night with observation and
Yeah.
record the change in brightness.
Yeah, so the picture, what's the range of periods of those? Because it looks like just a few hours.
Anywhere from 0.3 to 2 days.
0.3 to 2 days.
Yeah, there are sub-variations of the T Tauri, of the RR Lyrae stars, like the RV Tauris.
3 hours, or do you think?
0.3 days to 2 days.
0.3 days would be what?
Oh, gosh, 24. Yeah, that's several hours.
Right, so in a period of one night, you can actually
Mhm.
make a video of it, you can actually see it.
There's actually a family of different subtypes of those T Tauri stars.
Right.
So, but they all fit within that sort of tight pattern that keeps them away from all the other different types of stars.
Right.
So it's the T Tauri, those RI Lyrae stars represent a family of different types of different subclassifications, subtypes of variable stars.
Right, so my point is that even though these things Justin is showing us, these aren't necessarily the only things professionals can do. Amateurs can go out
Yeah.
and do this stuff themselves.
And just a few basic equations, you can even determine the distance of these globular clusters.
Right, it's within range of what amateurs can do.
Yeah.
I'm just curious, these mill ratios you're talking about,
Mhm.
do they have to measure about individual stars, or they're doing something collectively about the whole life?
They will look at different sections of a globular cluster. They'll look at one region on the edge, one region along the middle, one region in the center, and then averaging them out, and then we're making assumptions on that. Because it's a lot of stars to look at. So you do population samplings in different regions there to try to get an extrapolated, hopefully very accurate picture as to looking at the star spectra, looking at the strength in the lines, and determining which is stronger, the hydrogen or the metals. Yeah.
I am just curious that if there is a kind of comparison in the size of a cluster with time, it might be related to the expansion of the universe, and also it can explain if it is a what kind of cluster it is, like what is the flame, if they are deeper in space or whatever it is, because with the expansion of the universe, we can figure out how they are situated inside the cluster.
Well, if we look back in time, we can look at the globular clusters as they are very primitive in their structure. We're looking just the first generations of stars. with mostly just hydrogen and helium, then compare that with the globular clusters we have now. Get an idea of the age of globular clusters and the evolution over billions of years of time. Yes.
So at the beginning, you said globular clusters tend to be metal poor.
Yes.
But then there was a later slide where you said, but there's different populations of globular clusters, some of them more metal rich, some of them more metal poor.
They are metal rich, but they'll only be like maybe 1% to 10% the amount of metals we find in the sun.
Okay.
Because the type 1s tend to be mostly just pure helium. Well, they're helium with a little bit of carbon, and then there are stars that have a bit more carbon and oxygen. So they'll be metal rich, but still metal poor with respect to the sun. But there are some exceptions I showed where there's some of the star globular clusters have twice the amount of metals than the sun. So we're really looking at possibly discovering a third type of star clusters. Yes.
So I remember about 30 or so years ago, there was a big mystery about the age of the globular clusters. They appeared to be older than the age of the universe.
Yes.
And now they've done more observations and got Hubble's constant down better. What happened? Did the globular clusters estimate get younger and the universe get older, or how did they resolve?
As spectrometers have become more refined, as adaptive optics has become more refined, as we've had better precision in looking at the motion of these bodies and looking at having just bigger mirrors with better resolutions, looking at the spectra of these stars, they've been able to just simply narrow the age range from 8 billion to 20 billion down to like from 8 to 13 billion for the bulk of globular clusters. So it's just better in terms of the instruments and better resolution, and just better data looking at the spectra.
I guess my question was, which one won? Was it the globulars were way too old and they got younger, or the universe was way too young and it got older?
The globular clusters are not that old.
Okay.
Yes. It's like looking at Pluto. When Pluto was first discovered, they thought it was 10 times the size of the Earth because they thought it was that missing exoplanet. But as the technology got better and there was better and better imaging, they scaled down poor Pluto to a smaller and smaller body until it's half the size of the Earth's moon. Same thing with the globular clusters. They look at the spectra of these stars to measure distance. The timing got more precise. And with more light, the spectrums got sharper and clear. And that was able to narrow the age range. Welcome. Did I blow everyone's mind? Okay. All right. And that is it. So thank you very much.
Alrighty. So no DVD library tonight, right? So we'll skip that one. Or did you want to say something, Ron?
Yeah,
Okay.
I'll have it here for the next meeting. I've got it in the car already, so I had a long day. Didn't want to call it up here. But if you have something to drop off, please do. And I'll take care of it.
Okay, thanks,
We've
Ron.
got about 200 overall DVDs. And if you don't have a drive anywhere, we've got those too. And so.
Great, thank you, Ron. What?
I put, there's about 8 of those Sky and Telescope magazines up there in the upper desk up there.
Oh, where Chris is? Okay, yeah, well, okay. So, so at the meeting, after the meeting, when we get done here, we're gonna shoot up the Mod Pizza and get together and eat pizza and make ourselves sick in the middle of the night and talk about astronomy. So you come out here, you shoot up Middlebrook North, you take a left on, or west, since you're an astronomer, on Clear Lake City Boulevard, right in front of HEB, there's a Mod Pizza. We'll all get together there and talk about all kinds of things. So we're gonna take a break, and just like Rick just said, we had a donation of some Sky and Telescope magazines, and Rick, you said you brought about 8 of them.
Yeah, I brought about 8. I'll bring like 8 or 10 over the
Yeah.
next 4 months.
That's fine. So Chris is holding them up there. If you guys would like to have those, they're free. Just take one, and one per customer for now. And if there's a bunch left over, take as many as you want. We'd like to get rid of them. But somebody donated those to the club. Actually, it's Lester family donated those to the club, and we'd like to give those to anyone who's interested in taking them with them. So we will take a 10-minute break, and we'll get back together with the second half of our meeting.
Excellent. Yeah, because they explain.
You're wondering, well, that starts very reddish, it's very easy to mistake for being like a black car. So it ain't clear on the other side, because all the light is being dispersed with respect to the red light. So this is more chemistry of
Some of the special lights maybe.
Okay, we're gonna get started with the second half of our meeting. This is my favorite part. My favorite part here, get this thing out. I'm coming to your classes. I'm telling you. I'm going to come to your class and I'm going to stand up and talk during the whole time. All right, here we go. All righty. The Taurus molecular cloud. All righty. Did I scare off the rest of your family, Jeff? No? All right.
Yes.
Whatever. Okay, so the first image I'm going to show you was taken with this configuration of Sigma 17 to 70 lens at 50 millimeters f4. It's a Canon 450 modified, and it's going to be 18 10-minute pictures. What I'm going to do, I'm going to skip. I made two sets of my slides, the dark slides that you can't see, and then I went back and made brighter slides so you can see them easier. Okay, that is the Taurus molecular cloud. So you can look over here and you see the constellation Taurus. There's Aldebaran, that red star, is very characteristic of this one. And you see the shape of Taurus. This is actually the California nebula, but it didn't have anything to do with what we're talking about. But in between Taurus and Perseus and Auriga, right in the middle here, is this gigantic molecular cloud, known as the Taurus molecular cloud, which is the subject of this short talk. Do I need to wait for you two to come back so I can start over? Don't fall down. It's not worth it. Okay, we're talking about the Taurus molecular cloud. Yeah, there it is right there. See that big black thing? Got it? Okay, Taurus molecular cloud. Alrighty, so molecular clouds, a little few things about them. Temperature 10 Kelvin to 50 Kelvin in that range. Density of 1,000 to 100,000 particles per centimeter cubed. Gas state molecules, that's why they call them a molecular cloud, right? Dense enough to form molecules. The main gas is H2, but there's more than 150 other molecules have been detected. The difference is between this and the rest of the interstellar medium is they're dense and cold enough that they can actually form molecules. And when we look at them, we see them as dark nebula. Okay, so this is the same shot, the Taurus molecular cloud here in the background here. But what I want to draw your attention to, I took this same region here and blew it up. And this is still with the 50 millimeter lens, but then blown up so you can see it. But then this is the same region here, but this was taken with a 1600 millimeter telescope. I don't know why it doesn't say that on there. That's very interesting, missing that. Anyway, that picture is taken with a 1600 millimeter telescope, and this is LBN 782, and this is Barnard 7 up here, this dark nebula, and down here is Vandenberg 27. So that's part of, that's a blow up area of the Taurus molecular cloud. So as you would expect, since it's a molecular cloud, there's going to be a bunch of Barnard objects. This is shows all the different Barnard objects. Barnard is a catalog of dark nebula. And not to be outdone, there's another catalog, the LDN Lens Dark Nebula catalog, shows the Lens Dark Nebula objects in the same region. And back to Barnard, this is Barnard 8 down here, and then a blown up region of it. This is actually the original image, again, is taken with a 50 millimeter lens. And then this inset here, this is actually the same region of Barnard 8, but it's 18, sorry, but it's taken with a 200 millimeter lens. So same area, but 200 millimeter lens, 50 millimeter lens. Got that? All right. Any questions about that? Anyway, the Taurus molecular cloud, right? All righty. Anyway, next up, we got Rick Slater. First time he's going to do a presentation for us.
Shortest one you've ever done.
Yay. Guess people don't like the Taurus molecular cloud. I think it's cool.
I thought
It's really cool. I mean, it's this big dark area in Taurus. It's really neat. So, what's that? Oh, it's coming. Stand by.
So these are all.
Oh, she's got a question. What?
These are all just like Canons and Nikon lenses that you put on different cameras or.
Were you paying attention?
I'm listening.
Okay.
There's a whole thing in this.
Let me just go back and get my entire presentation again.
No, I'll talk to you later.
No, hold on. How come this thing won't back up now?
No, he's ready.
No, I gotta.
Usually
Okay.
15 minutes.
No, hold on. That's why, because I didn't get any questions. Okay, so Linda, the one in the background is taken with a 50 millimeter lens on a modified DSLR. Okay. This one up here in the upper left-hand corner, that's taken with a 200 millimeter lens, but it's actually on an astronomy camera, not a DSLR.
Oh.
So you actually, if you look at the quality difference, I mean, you can really see this dark nebula with the astronomy camera.
Yes.
You'll always get better results with an astronomy camera than you will with a DSLR, but it's also a 200 millimeter lens versus a 50 millimeter lens. But back here, it's okay. You know, when I watch TV, I sit there and rewind it back and forth trying to understand what they're telling me. Okay, this one here, the background one is with a 50 millimeter camera lens on a DSLR, right? Huh?
You got that with 50 millimeters.
50 millimeter, you know.
And you mount the camera, like it's rotating.
Man, you weren't paying attention at all here.
I told you on pizza, over pizza. Oh, okay, cool. Oh, wow.
Man, you really weren't paying attention. Okay, look, that's that's a 17 to 70 lens, but it's set at 50 millimeters, right? And there's a DSLR there, and it's on a telescope mount.
Is this the part where I said I wasn't in the room?
Maybe you weren't. We'll use that as an excuse. Okay, so you see that?
Yeah.
That's how this picture was taken. See at the bottom, it says first image configuration at the bottom.
Yeah.
First image configuration. Okay. Okay, now, so that, okay, here, I'm trying to answer your question. All right, so this background image was taken with a 50 millimeter lens on a DSLR on that camera mount, right? The one in the lower left-hand corner was taken with a rich accretion, like your buddy over there got, but 1600 millimeter focal length rich accretion. And that inset, I'm showing you this blow up of that same region there, but taken with a 1600 millimeter rich accretion telescope and with an astronomy camera, not a DSLR. See, so hopefully, yeah, it's a much better quality picture. And yeah, if you want to get serious about this, you want to use an astronomy camera, not a DSLR. But okay, you got it? Does that answer your question? Okay. What?
Forward through your slide for a second.
What?
Next. All right, that one.
Yeah.
Did you do that with a color camera or your mono?
Mono.
Okay.
My astronomy cameras are all mono.
Okay.
Mono. We do not do color astronomy cameras.
Okay.
That's
Just check.
yeah. I won't. That's why have an astronomy camera and then get a color one? Like I might as well have a DSLR, right? So sorry, but I know there's a lot of guys in the group that got a color astronomy camera. You have my sympathy, but I think I'm the only one. Well, me and Rick. Where'd Rick go? Rick's got he's got a monochrome too. I think we are the only two in the whole club that have monochrome cameras. Okay. Any other questions? All right. Fine. Oh, sorry. So here's Rick. How I bought my first telescope.
Okay, I'm new and this is my first one. So anyway, and where do I push the button here? I got,
You push enter to go forward.
all right. So anyway, I joined about a year ago, and I knew I wanted to get a telescope eventually, but basically I spend usually about a year. I spent over a year when I got a cello.
You have to stand in front of the computer and that microphone.
Oh, all right.
Because the microphone is in that laptop, and then the room mic is right there in front of you.
Okay. If I'd been here longer, I probably would have paid attention and known that.
I announced everything when you joined.
Yeah, thank you. Okay, so at any rate, I wanted to get one, and I knew that I was probably going to research it for a while, and just to give you an idea of what this trip was like, this is about the best symbolic description it was a real maze trying to get there. Next. So what I thought I wanted before I joined the astronomy club, there's a picture of it there, either an 8 or a 10-inch Kesskring. And the problem was I just wanted it because it looked cool. Now, it's still a great telescope, and I could have ended up there depending on how the research went and everything. But that's certainly no reason to buy a telescope. And I really learned that over the last year. I'd read the JSC Astronomy website, and it kind of reinforced it. And they said, and I don't remember what the real words are, I didn't bother to look it up, but it was basically wait a year, speak to members, go to star parties before you buy a telescope. So take your time. And so hence began, it was really 11 months before I actually bought the telescope. And to be honest with you, it was about 3 months, 2 to 3 months before I bought all the extra stuff that went along with it. Okay, so I began, and I'm not going to go through all of these things. You can kind of read through them, but there's a couple I'll highlight. I began by putting together a list of comments from members. I went to star parties. I asked people. I hounded Doug and for information. And anybody who had something at one of the star parties, I would go and try to ask questions so that they'd still talk to me the next time I saw them. And I ended up with about 50 good suggestions. And there were 4 that really stood out, 2 of which Doug gave me. And the first one is probably the best one, and that is don't buy a first telescope that's too complicated to set up and operate. Don't try to go to the nth degree on astrophotography or anything like that. Start small and work your way up. And it's definitely the path I would have taken if I had not run into somebody who could help me along. And as you get older, you're not going to want to have a heavy telescope. I talked to numerous folks that have quite a few telescopes, to maybe 2 or 3, and they've got one big one and they hardly ever use it anymore because they're 78 years old and they just don't want to carry it anymore. They're afraid of it. So I considered the size. Another one is, and this is a direct quote I think you'll find from Doug. A color camera is great for photography, but a black and white camera with filters will do much more. It's also expensive and much more difficult. And I will tell you, yes, it is. And but sort of my Achilles heel has always been I want it to do everything, which means I want to explore, and it always ends up the most complicated. But I also realized I didn't have anybody to walk me through that whole process. And another one that came up, and I just love this one. About 85% of the way to after I got in the scope and I was finishing up, talked to Doug, and Doug said, hey, be careful when you buy your filters, because 6 nanometer filters are not going to cut it anymore. Used to, but not with the air quality we've got today. You've got to go with 3 nanometers. So that actually became really important. Anyway, I ended up with about 50 good suggestions. From that, I put together my own research questions that I knew I needed to dig into. And I won't go through those, but there were a lot more than I've got here. Okay. So I ended up with a list of requirements. Before I made a few trips up to land, sea, and sky. It was the only place I knew I could talk to people about telescopes in Houston. And I went up there, and I ended up with, these, and I won't go through all of them, but, a telescope, small, portable, something that I'm going on to 71, and by the time I'm 80, I still want to be able to lift it. So that was important to me. I actually looked at some YouTubes, which I spent a lot of time on, and they had one that that said, hey, here are the nebulas and constellations that you can image. And this is how big the telescope needs to be. And I came up with something roughly 300 to 800 millimeters. And I won't go through any of the other technical ones, but I will mention this. I knew if I was going to do something a little more complicated, I wasn't going to be able to pester everybody and actually put it all together. I was really going to need somebody who had what I thought I was going to purchase. So I needed a mentor, but I had no idea where I was going to get one. So I was pretty sure I was going to end up with that first telescope you saw. And I also knew that if I went to a store, I wanted a technical salesman capable of explaining things. I did not want just a salesman who would point me in one direction or the other. Those became two of the most important things that came about. So as I went to Land, Sea, and Sky, and the first one I've got up there is Find a Mentor to Guide You. I ran into, first person I went into, they said, hey, if you want to buy a telescope, you have to talk to Chris. I think it's Montemeyer. And he is the Takahashi rep for the country, ex-teacher. He's a retired teacher. Took this on, has about 10 telescopes, and he's been an amateur, as he puts it, for about 30 years. And of course, he's much more educated on Takahashi. So I went ahead, I was talking with him, and now I need these glasses. Yeah. And I talked with him, and eventually he became my mentor. And the main reason was the telescope that I wanted to buy. And he didn't push me in any one direction, but he said, here's what each one of them does. Make your own decision, decide what you want to do. And I made a decision. And when I did, he said, well, I got to tell you, Rick, he goes, now you're talking to me about some of the other, the add-ons besides the telescope. And I happen to have this exact telescope. And in this telescope, and he's here putting it together, he said, tell you what, he said, I'll tell you exactly what I have. If you choose to buy it, it was all mainly ZWO equipment. He said, I've got the exact same scope. I'll walk you through it. I'll put it together for you. And he did. And right here is when he was putting the thing together. And so my next thing is, as you're doing that, spend time and learn the terminology on the telescopes. And that, I have to tell you, the first thing he told me was, if you're buying a quality scope, they design the scope for what you're going to use it for. So you got to decide. And by then I had decided I was going to do astrophotography. I wanted to be able to look through it too. And after talking with Doug, I was definitely going to go black and white and have a filter wheel. So a couple of the examples that come up, you can have a doublet, which is basically 2 pieces of glass. You've got a triplet, which is 3, and a quadruplet that's 4. And some of the differences there are the doublets are basically good for viewing. And one other thing, and the only reason I'm kind of emphasizing this is kind of the level of detail I had to get to really make a good decision. A doublet only has to be sharper than your eye to resolve. And your eye resolves about 14 microns. Hence, they can make it resolve 12 microns, and it's going to do the job. And in the case of Takahashi, that's basically how they design the telescopes. The other thing is, you'll find that they'll say, hey, these are much cheaper than these expensive ones. That's basically why. It's much cheaper to make the lenses so that they only have to resolve 12 microns instead of the 12 microns. It's much cheaper than on a triplet or a quadruplet that has to resolve about 2.4 microns. And in fact, my camera is about 3.76 microns, so they just had to beat that. Those are some of the things that you want to have an expert who actually will walk you through. Why did I buy Takahashi? Because they sell them here. They have 2 or 3 technicians that if something goes wrong, they can fix it right in the shop. I just drive it down. It was a little more than expensive than 2 or 3 of the other really good brands. And I probably wouldn't be able to, in fact, he even told me, if you bought one of the other brands, there's a good chance you're not going to tell much difference, if any, with the Takahashi. He goes, there's like 3 or 4 really good brands. But I chose to do it down there for 2 reasons. One, initially, because I could get it fixed there. 2, because when he said, hey, I'll tell you how it is, what I've got, I will put it together for you, and you can call me if you got questions on something. And I've called him several times throughout the whole process. So at that point, I was able to do what I really wanted to do, which was not spend 10 years working my way up to doing what I really wanted to do. I was able to do it, well, not now, but hopefully within 6 or 8 months, I'm beginning to do it. And so the other thing is take a lot of time to figure out what you really want to do. I spent a couple months just thinking out, do I just want to look through it? Do I want to, what do I want to do? Do I really want to get into the astrophotography? And in the end, I started looking at the imagery and everything, and I did. So that one of the other questions I asked him before I even purchased the thing, I said, exactly what kind of images of nebulas can I get with this? It's a baby Q. It's about 450 millimeters. What do the pictures look like? And he said, with the exact same scope, he had some pictures, and I brought one. And let me just send them to you. So he did. There we go. Got the California Nebula there. And I saw that and I said, I think I'm getting somewhere. Small. I think it's going to work out. At the same time, though, the next thing I thought about was, hey, with this camera, am I actually going to be able to blow this thing up? Am I actually going to be able to zoom in and see more detail? So this is what I got when I saw that. And if you look in the little blue or purple rectangle there, I blew that up, and this is what I ended up with. And when I saw that, and he admittedly says, I'm not as good with, was that Axel Pixel processor? I'm not that good with these images. I kind of have to disagree with him because I thought these are pretty good. But he said there's people that are actually better. But he said, I'm not too bad. He also sent them to me where he got rid of all the stars, which made it easier to kind of look at the nebula too. So after that, the biggest thing that I got out of all this is take your time, ask a lot of questions of a lot of different people, because I got a lot of really good stuff that he had never told me. Chris never even mentioned, which I'm actually doing, and there's a few more things I have to buy, and I'm going to go ahead and get them based on what some of you folks out there gave me. But get a mentor. If you're going to try to leapfrog, then you need to get a mentor. You need to somehow get someone who has the same setup you have, who's willing to work with you, because there's no way to go to a star party and put a few pieces of the puzzle together. So in the end, that's my telescope. It's about 12 pounds with attachments. It's a 450 millimeter native with an extender. You can get up to 680. And I'm not sure. I still think the picture he sent me was with the extender. I'm pretty sure he had mentioned that. It's called a Baby Q. It's an FSQ, which is a high quality. basically, it's what we call the quadruplet. And of course, when you go to a triplet, what they're really doing is they are making sure that the red, green, and blue all focus at the same point. And that's huge. And in the doublet, you don't have to do that because your eye sees what it really wants to see. So you don't have to go ahead and do that. And then, I put some other details in here, went ahead and got the filters, the parts. I'm waiting on an autofocuser, but I'll be able to use it without the autofocuser, so that won't be a problem. And the thing sits literally, it comes up to my waist, which is how you do astrophotography. You want it as low as possible so the wind doesn't blow it around and everything. So that's how I ended up with this telescope. Now the next year we'll be starting to use it and see if I can do things without making too many mistakes. So my first telescope.
You didn't mention the investment,
What's that?
what that represents.
How much?
Dollars?
Yeah.
It was less than my cello. It's less than my cello. It's about 12,000. So, but I looked at it this way. It's an investment that I'm going to get 10 years out of. I've also been planning on retiring for 25 years, so I've been saving. So it wasn't really a big deal. But although I will say my wife mentioned, she said, so we all done now? She said, is that it?
You've been married how long? And
Yeah.
Take a photo with a long exposure, you might play the cello.
No. And here's the worst part. 15 years ago or so, a little more longer than that, my daughter was taking the violin and I was actually working with a couple of groups just as an adult, just helping them with music and passing out stuff. And so I picked up a $250 cello, and the way it was described to me was in China, they make these and they make them in a big factory. And see, over on this side, they make brooms. And on this side, they make cellos. I literally had to have a friend of mine from Armand Bayou, who's a wood carver, actually carve the neck because it was beyond usable. Then I bought another one that's a little more expensive. Then I bought one that was more than this. And I haven't used it for 3 years. And my daughter's on me, hey, you need to use it. I'm thinking about just, selling it because it's just sitting there. But I got 15 years use out of it. So if I get a good 10 years out of this, I'll be perfectly happy.
You can buy more telescope equipment.
Well, and honestly, I will tell you this. I got one of these great courses after Doug here was doing his radio, his radio astronomy. And I got one in the great courses. They have one on radio astronomy, which is absolutely fabulous.
It is really good.
It's excellent. And I'm hooked on understanding it, but I'm not hooked on buying one right now. I think I've got my challenge in front of me, but I'm kind of interested in going that route too. So instead of maybe buying another telescope, I may end up heading in that direction at some point. For that, I probably will go ahead and sell the cello and use that money for that. Anyway, any other questions? I hope I didn't bore you. It's just.
Can't wait to see what you do with it. Yeah. Let's see some pictures.
My wife too. She mentioned that same thing.
Let's go.
All right, thank you.
All right, thank you, Rick. Next up, Al is going to bring us tonight's What's Up in the Sky.
Hello. So let's see the down arrow or just the enter? No? Doug?
How'd you do that?
I just hit enter. I went down first.
Went to the beginning of the whole thing. How did that happen?
I went down arrow and it didn't go.
No, you want to hit the enter button. Here. Yeah, no down arrows. Enter and backspace.
Oh, backspace.
Yeah, sorry. Yeah. You guys get to see Justin's presentation again, in case you missed it the first time.
No way to skip ahead. Page down, page up?
I don't know how to do that. I don't want to take the risk. Any second now.
Well, so I am doing what's up in the sky for December, and I'm also going to do a little part in what's happening in astronomy today or this month. So the very first thing to go over is meteor showers. Geminids? That's going on right now. So these are the peaks. So a lot of meteor showers go for about 2 weeks almost, but there's always a peak time. Ursids, I've seen both the first two. The quaternids, I've never really seen, and that happens late or early. The peak is in early January, but I put it in here because it spans some of December. So this explains sometimes why when we're out doing a lot of observing, we see a lot of meteors because there's showers going on all the time. My very first object, so for things that are up in the night sky. So I always start off with binocular objects. So Orion's Nebula, of course, with binoculars, we never see it quite this wonderful. And of course, it's in Orion. How many people have seen this nebula with binoculars? Okay, quite a bit. So the next one is the Beehive cluster. One night I was out and I was looking at this portion of the sky here. This is Cancer. And I mentioned to some people, I go, what is this thing coming up over here? Well, I'd never really looked it up. I have a telescope, so I don't normally look at a lot of visual things that are so bright like this, but it was really exciting. So I trained my telescopes on it, and it was neat to look at even in a telescope. But so these are two binocular objects you can look at. Of course, this is visual. You can see pretty naked eye. Next object is Eskimo Nebula. So this is a popular one. I like this a lot myself. This is, I believe this is in Gemini. I was using my 25-inch telescope early this spring. I had at El Dorado 2 of the best nights I've ever had there in several years. And I saw this with a lot of the structure. Eskimo doesn't look so blue in a bigger telescope, but I saw quite a bit of the structure and I could see these ovals inside the center. So it was pretty exciting. In average skies, even in a 25-inch, you don't see a lot of the structure. The structure looks like little fingers, little rays sticking out from the center. So I like to look, an object like this in a larger telescope you can look at for 5 or 10 minutes. So this is one I have not looked at. This is PK205, Medusa Nebula. Doug, have you looked at this?
Yeah.
Telescope-wise? Does it come out pretty nice?
Yeah.
So it looks like it has low surface brightness. And if you just imagine turning this into like a whitish color instead of all the pretty colors, that's probably what you'll really see. The next object I have looked at, IC443. And this is very similar. You can see a little bit of this cloudy effect off to the side and then a little bit of this ring in the lower right. So these are mid-size objects. You can still see these with some pretty good-sized telescopes, 12-inch or so.
Hey, Al, hold on. Can you tell everybody the difference between the image on the left and the image on the right?
Oh, did you know why that was there?
No, I just want you to.
I forgot.
Yeah.
So the image on the left is what a pretty simple photograph looks like. And the image on the right is a fully doctored, photoshopped image. That's what the article said that I took the picture from. This is from Wikipedia. That's where I get some of the color images from. Why? Because it's not full of a lot of controversy. Go ahead.
Is that what you?
Go ahead. You think the right is narrowband?
Yes.
Okay.
Okay, that's what I was, okay. You guys, the one on the right is a narrowband image. The one on the left is an RGB image of the same target. That's the big difference between. I just wanted to point, that's a really good example.
Right, but what he didn't say is, in the right image, those are false colors because in the real image you see real colors, and in the right image you have to put in the colors that you like for that particular filter.
Absolutely, all the narrowband stuff is false colors. Absolutely, you see all the different elements within that.
So did that fall under the category of fully doctored Photoshop image?
Yeah.
Okay. No, I love it. Your narrowband pictures are wonderful. I'm very jealous that.
Well, he was talking about narrowband filter. That's what I thought.
So this is ARP 82, and you can also find them under NGC 2535. That's handy because some telescopes don't have an ARP list, but only have an NGC list. So if you're trying to find this. Now this gets into the more obscure and smaller objects. I believe I've seen this one recently. The picture on the right is really neat because that's more of what you see. I like this image on the left. I can't tell you why the colors are purple and green. Obviously there's some kind of false colors. Maybe it's a James Webb or a Hubble image. But the next one is ARP 78. I didn't have a true to life picture of this. I could have pulled it out of the ARP book as a black and white. But this one's really cool because they're two interactive galaxies. And I believe, let's see, 70, 72. So this is really cool because that's like an elliptical, the 770, and it's probably gone through the 772. And that's why that arm is distorted in the upper portion. And why is this neat? Well, when you can see this in a telescope, you want to look at the picture in the book and then imagine you're seeing those smaller portions that are faint. So you can get the real feeling of an ARP galaxy, which is an interacted galaxy, two galaxies that have interacted together. That's what I find. You can look at an object and try to imagine seeing it, but many times you have to know what you're looking for to actually kind of visualize it. I don't know if we're imagining it or if it's using the averted vision that really comes in handy. That's what I think it really is. When I know that there's something obscure in an object, I use a lot of averted vision, and I just let those photons really hit my eyeball for quite a long time in order to really see those less defined parts of the object. So now we're going to go on to, I didn't put a slide in for this, but what is happening in astronomy? So every month I'm going to peruse what's going on in astronomy in the month. And this is one I found very interesting. And this is a very large red giant, one of the largest. And the reason why they use this one is because it's so large. So it's easier to see some of the surface. And it's called XX Trianguli. I don't know why it's called XX. I think it's because there's many of the stars located in Triangulum that are named this. And I'm going to show you a video in a minute, but some of the details are Stella is a robotic observatory that has two 1.2 millimeter telescopes. I think to do Doppler imaging, you have to have two telescopes. Is that how they do it? And then they analyze the difference between the two telescopes in order to see the Doppler shift. I don't think with one telescope you can see Doppler. And I tried really hard to try to learn a lot about this, but boy, I did not have enough time. So what I can tell you is these dark patches and the light part, what they do is, if you can imagine as this star is rotating. Oh, the other thing they found is they took a red giant that they thought had a lot of rotational speed. That's because in one evening, you want to try to get several images. You don't want to have one image one night, one image another night, maybe a missing image. So they wanted to have more images of the changes in one night period of time. So they had that operation since 2006. And so you can imagine during the rotation, there's a drop in the Doppler shift. So they will see a Doppler amount of a certain amount, and then it might go up and it might go down. And during that time, then they imagine through the trickery of math in the computer to create this semi-false image. So they're not actually seeing this on the image of the star. Like they haven't blown the star up so much they see this big circle. They're creating this image in software. But it's very interesting. So I've got a leap ahead here. And so this came from YouTube. I tried to, one more enter to get it to play. I didn't cut out the sound, but I might be able to quit early after we've seen it.
It started 2 minutes in.
In my video, I cut all this out, but anyway. I couldn't get the video to, oh, it's not going to go. That's terrible. Maybe it quit. Let's see. Let me go like this. Is it going to go?
That's the next slide.
We'll go back and see if I can get it to play. Anyway, you can go on YouTube and look up this star. This is all recent stuff from this month. And there's a picture of it spinning in a circle around and around and around with the spot changing size. So the slide I showed you before showed different time periods with the spots changing. And they call them star spots. Now, I didn't understand the difference. So we call them sunspots here, but the name of our star is called the sun. So I don't know if they call them star spots because they're talking about any star, or if they are particularly large, because these sunspots are almost, I don't know, 1/10 of the size of the star itself. So I don't know. So the next object that I found that was interesting was the Meerkat telescope. I want to learn more about this telescope. It's not a terrifically giant telescope, but it takes some interesting pictures. It's an array, I think, a radio array. So then this is another created image, but they found these things called odd radio circles. And these rings can be, I believe, many times the size of our galaxy. So it could be 10 times the size of the Milky Way galaxy. And so they're huge, but then I think that they have found smaller circles, but these being so large, they call them odd. And to this day, they don't know yet what is causing them, but this has been one of the largest ones they found. So they thought this month this is peculiar or different. And so what I did find on the internet is there's a lot of information that's posted without an actual research paper that's fully completed to a conclusion. A lot of people nowadays are posting, I would call pre-information, pre-conclusion. Like, you know, it used to be you produce a paper and you would fully be getting to the end of all your research and you would publish it. But now what's happening is you're finding a lot of early information. Maybe that's so they can get other contributors to bring up information that's related to their paper. I'm not sure. So here is a third item. So since 2018, 16 megapixel wide field camera they've been using on this, I can't pronounce that, Ocean telescope. I don't believe that's the big Mount Palomar telescope. I believe this is another like 1 millimeter or so telescope. A lot of the larger telescopes now have 2 or 3 smaller mid-sized telescopes that they use for other type of secondary research. And I just found it very interesting because 10,000 supernova, not 100, not 1,000, 10,000. I don't know. That just seems like a large amount. But what it seems like is they have some very good software to detect all these supernova. I've seen in the last 5 years 2 or 3 supernova in some local galaxies or relatively close galaxies. And I thought I would never see one. And so they're maybe a little bit more abundant than I thought. And so it's pretty interesting. What I have found about seeing supernovas in galaxies is most stars around galaxies look like a fairly, diffracted star, where you will see a little bit of a blur. But all the supernova in the galaxies all look like the most pinpoint star that looks more sharp than most of the stars you look at as you're looking at galaxies and other objects. And so I find it fascinating. Let's see if this video will happen. This is a video of, one more time. Oh, this one's working. Maybe the other one will work. So there's 3 types here. They were talking in the article about 2 different types, the exploding white dwarfs and the collapsing massive stars. But there's this third one that they didn't talk about in the article, which I don't know anything about. But you notice it's much more rare. You see the green ones almost not very often. And then you see them sporadic sometimes. But they're everywhere. So not so uncommon. Doug, do you think we can get back to that other video to try it one more time? Because I think that's the coolest thing. Oh, one more thing. So this leads to a little discussion. So above is the new web picture of the Sombrero Galaxy. They have a thing called a mid-infrared instrument. I don't know all the James Webb instruments. I haven't studied James Webb that much. And then the picture below is a traditional image of the Hubble. And if you look through any other telescope, you'll see more of that image. And so there's this dust lane in here that obscures everything. And then the upper image shows that dust lane kind of nullified or disappeared or put in the background so that you can actually see the clumps. And so what I thought was very interesting was they say that Sombrero doesn't have the most, but a lot of globular clusters, around 2,000. So I thought this would be great. Let me go and study more about this. I want to see like if they have pictures of these globulars in Sombrero or this or that or the other thing. And what I found was like 5 pages on Google of nothing but people using what just came out from the James Webb to have themselves looked at on the web, so that I couldn't do any research at all. And I never found any research or any information about globulars in Sombrero because so many people are posting this, even young women trying to get visibility on their webpage or on their Instagram account or whatever. And I found it sort of disturbing that the research end of the web is getting pushed away by social media. Sorry. Doug, can we go back to that other video?
People are interested in astronomy? I don't know.
No, I think they want people to come look into their website. There's no way to go backwards?
No, I think we can move on.
That's it.
Yeah, we're already at the end of our time.
Well, thank you all. I hopefully will bring some more neat objects to you in the future.
All right, next up, David with Star Party News.
Real quick, when you were talking about narrowband, is that also the near IR imaging that you were trying to do?
Oh, now that's another thing.
Okay.
But that's really cool also, the near.
I mean, that's what I thought that was going to be an IR. All right, this is going to be very quick. Keep us all on track. Past events, I had November 12th at UH Clear Lake right here. November 14th, it was all done in 1 week. Thursday at Armand Bayou. November 16th at Magnolia Creek. And I really thank everybody who attended those. Life got crazy for me and Connie in November and December, and it still sort of continues. I was not able to make any of these events this time. I think Clear Lake, I simply just wasn't feeling good. We do have on January 11th, Saturday was our new postponed, as our new date for the Evelyn Metter. And as I think we've got that worked out from 7:30 to 11. Orion should be up, so that should be a real good cloud pleaser as long as the events, as long as the clouds stay away. All right, on November 12th, right here at University of Clear Lake, I really appreciate Andrew Olson. I don't know if you're in the crowd, but I appreciate you supplying the pictures of a couple of images. And then, of course, that looks like it was Reed Klotzer's shot of M27. I only got those three, but we got Doug, Reed, Stan, Richard, Brandon, Justin, Andrew, and Mark. Then on the 14th, Armin Bayou. I'm happy that one actually worked out. We weren't sure there for a little bit. We weren't exactly getting straight information from them, to be honest, but it all kind of, hopefully it all worked out in the 11th hour. So they said they had 30 plus people plus Armin Bayou volunteers. Again, I thank Bob and Leslie Eaton, and again, Richard Slater for pictures. So Stan Lamb, Bob and Leslie, Mark DeCellis, Reed, and Richard. If in these three presentations, somebody was there that I missed, I apologize. Just let me know. I'll try to make sure we give you that credit. Pictures there of people working on the scopes. And then of course that center one here, Reed's working on that Sea Star. I recognize Mark's scope over here. I'm not 100% what's going on over there, but obviously some good discussions are going on. Again, some more here. Decent sized scopes. Good to see people looking through them. And then on the 16th at Magnolia Creek, that was also an 11th hour. Can we pull this off and still make it work? And the answer was yes. Again, thanks again to Bob and Leslie Eaton, Richard Slater again for the slides. Chris Randall made that one as well as Doug. And then there's one more. That golf course has got a really nice open view to the east from the south. From the east to the west of the south. So there's you can't see much to the north because of Houston's light plume and of course the clubhouse, but it's actually pretty unobstructed and not a bad place. Some may not get this, but since I'm a lunar imager, I always find humor in the particular one. Yes, it's a tortilla. All right. Thanks again and see you next year.
Okay, I know we're over our time. Okay, I didn't want to leave you guys without a radio astronomy talk. Somebody said something about that earlier, so we'll make it quick. Fun at 1420. Whoever's got the door prize or bucket, if you can bring it down here, to really help out. Thanks, Chris. Okay, this configuration, talk about this. 2.1 meter dish, f0.4. You know, in telescopes, we have like f10, f8, and stuff like that. Radio telescopes, 0 point something. 1420 megahertz cylindrical waveguide horn's got a 6 to 7 inch flare. The reason I'm telling you that is because if you look at the SWR, if that means anything to you guys, 1.19 is really good SWR, and the radiation resistance on this is 50 ohms. It's perfect. So it's right at what it's supposed to be. I should put that up there. But when you're trying to match this to a 50 ohm, Rick, are you paying attention? I'm doing this for you, man. Yeah, you said you were interested in radio astronomy, right? Anyway, so this one actually has a 50 ohm match, so it'll actually match your LNA just perfectly. So when you get around and doing this, the flare actually made a big difference. Okay. Then I'm using the Nolec H1 LNA because it's got really good low noise characteristics. AirSpy Mini, that one's, I've tried several of them. That's actually the best one I've tried. Very short USB cable because you're gonna get interference on your USB cable from the AirSpy Mini or from your SDR software defined radio to your computer. So the shorter your USB cable, and believe it or not, I'm sitting in the computer right under the dish. That seems to work better. I used to run long cables and all kinds of crazy stuff like that. It actually works better to put that. And also, if you close the lid on the laptop, the graphics turns off and makes the laptop quieter. Okay. So anyway, hope you got that. Anyway. All right. So the Facebook, if you're interested in radio astronomy, there's a Facebook amateur radio astronomy group. If you want to join that, there's about 10 people in the whole world that are on it. So, great. But anyway, but if you're interested in it, it's pretty cool. There's people from all over the world that are involved in this thing. They also have, varying degrees of English capability, but it's a lot of fun. There's very few people involved in this that are interested in it. But anyway, they've been talking about this new software. One's called IF Average to CSB. CSB is kind of what?
I didn't get a picture.
Get a picture of what?
Can you go back to the last slide?
Rick, pay attention. You and Linda need to talk after.
Oh, okay. No, sorry.
He's going to say, was this taken with a radio telescope? That's what he's going to say next.
Here, I'll take a picture of your backyard telescope. No,
Yeah, that's my yard work
Obviously, a
capability.
radio telescope takes an image of a radio telescope.
Just take the picture so we can move on. Are you done?
I'm done.
Thank you.
No, you didn't take that. Did you take that one?
That's the one I needed.
God,
That's the
you
one
guys.
we were on.
All right.
Thanks,
Anyway,
David. Always fun to be your friend.
okay. Let's move on. Okay, so these guys have been talking about this new software. One's IF Average to CSB. CSB is comma separated values. And then there's this Rhine arm graphics and the combination of these two, you'll see what we can do with this. So when you do this out in your backyard, you're going to find out that your baseline of your data just goes all over the place. The top graph is of over a 24-hour period. And what's going on is the gain of the system just moves up and down and all over the place with temperature and clouds going by and day and night and all this stuff. This little bump over here is actually the Milky Way going by, but this is a 24-hour thing, and the gain's just going all over the place. When you plot each of the gain, each one of the plots, they're separated by 5 minutes, and you can see the gains just all over the place. The baseline of this thing is everywhere. So what this software is going to do for you, this is a declination 47.5 over a 24-hour period of time. What the software is going to do for you is it is going to normalize the all of this. Instead of it going all over the place, it's going to normalize it to baseline it all so you can actually do something reasonable with your data. That's the point of this. So this is a 3D plot with Rhine ARN graphics using the CSV files that this thing produces. And this is, along here, this is right ascension in hours over a 24-hour period. This is amplitude, obviously. And then this, along this axis, is frequency, okay? So I'm going to show you two different views of this. You look at this view, and you look at this view. That's a side view of the same thing, okay? Front view, side view. When we look at this, these humps here, bing, 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 right there, 1, 2, 3, that's evidence that our galaxy has multiple arms. I've told you guys this before, but those different frequencies are evidence that when I'm looking in that position, I'm actually looking at, I see, like when you look at it visually, you see a bunch of stars, but when you look at it with a radio telescope, you're actually seeing 3 different arms of the Milky Way galaxy. They're just behind each other. You can't see with your eyes, but you can see with a radio telescope.
Spiral arm.
What?
The spiral arm.
Spiral arms.
Of the galaxy.
Yes, multiple spiral arms. When you look at it with a radio telescope, this thing right here, David, is actually you're seeing through it. You're seeing the 3 spiral arms. You see it right there, but the radio telescope is showing that there's 3 of them there because there are 3 different frequencies. So that is, we're going to talk about this in a minute. That's the summer Milky Way right here. And then you see, look carefully here, there's bing, 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 there's 3 there. You guys see those? Those 3, that's the winter Milky Way, okay? Now hold on for a minute. Don't let that freak out. Now this is looking at the side view. Of course, this again is hours this way, and this is frequency this way. So now you can see this is the summer Milky Way here. This is the winter Milky Way, and then we're going to talk about what this little doodad is here. But there's something else kind of cool here. There's 3 little bumps down here. See those? 1, 2, 3. Can you guys see that? That's actually the interstellar medium when you're not looking at in the plane of our galaxy. When you're looking out of the plane, those are actually bumps of clumps of hydrogen gas in the interstellar medium. And when I posted this, the guys on the group, nobody has seen this before. I don't know, we just got lucky or just dumb luck or whatever. But we were actually seeing clumps of interstellar medium now with this new software brought this out, which I've never seen it before with any of my other processing.
Interstellar or intergalactic?
Interstellar. It's not intergalactic because it's within our galaxy. Yeah, interstellar medium. And these are bumps within the interstellar medium. Okay, so this you know, when you have a whole bunch of planetary programs when you do visual astronomy. One of the radio astronomy things, and if you guys are interested in this, is Radio Eyes. The software package costs $40, and you can use this for doing various radio astronomy projects. So this is my beam here. It's at 47.5 degrees declination. This is a summer Milky Way. So you see Cygnus there, and you see Aquila over here, and this is a winter Milky Way. There's Auriga and Orion and Gemini over here. So the summer Milky Way and the winter Milky Way go over every day. But the thing is, you know, we're turning around, we see both of them. It's like if you're standing underneath the St. Louis Arch and you looked at it and you look, okay, here's the summer Milky Way. I turn around and then here's the winter Milky Way. We're in the middle of it. So the summer Milky Way and the winter Milky Way go over us every day. We call one summer because you can see it at nighttime in the summer. And we call the other one winter because you can see it at nighttime in the winter. But in this, imagine this again, like this is like the St. Louis Arch again. Over here, this is the summer one, but this is our plot, the summer Milky Way here. This is the winter one. This is the winter here. And then in between this, you see this kind of shelf looking thing. This is actually the beam right along here. You're actually seeing this, this is still within my beam. I'm still picking up some neutral hydrogen there. Okay. And then this is a top view. One of the other guys in the group did this. He took my data and he made a top view in the same graphics program. I don't know how he did it. Somehow he piddled around with it and got this. But this is a top view of the same data. Alex Pettit, he's a really good guy in the group. Okay, so any questions about that? No. Yes, one.
Remind me again, the antenna is not moving.
Right.
You're just kind of doing the aerocecal thing and you're waiting for the heavens to move and move in front of it. Okay.
Exactly right, David. The telescope can move in declination this way, right? Just trust me. Okay, it can move in declination, but it cannot move in right ascension. Okay. So when the Earth goes by, I just pick up whatever in it. And because the beam is so wide, you know, you think, wow, 2.1 meters, well, big deal. The resolution at radio wavelengths is 7 degrees. So like each pixel is like 7 degrees, which is huge. So I get a long time on one sample. My sample is like 5 minutes long integration time for each one, but that's way smaller than my beam width is. Does that answer your question? Okay. Any other questions? Okay, good. We can get out here and go eat. Oh, there she is.
I have a dumb question.
Oh, good. I love it.
Is this software doing some kind of optimization?
Yes.
Or attenuation, because the peaks are so clear.
Okay, Dr. Masood, what it is, okay, the peaks are my data. Yay. What's cool about this is that this original data, the baseline of the data, look at this. That baseline is going all the way up and down. See, it's going all over the place. The peaks are good though. I mean, I've got almost 2 dB, which is a big deal in radio astronomy, 2 dB of signal noise ratio. So I've got good peaks. The peaks are great. What the software is doing for me is normalizing all that data to the same baseline. And something else it does, this is kind of a little different. It actually whacks off anything that's lower than the baseline, which I really like because these software-defined radios, Rick, actually have a tuning problem and they actually have negative amplitudes, which is impossible. So it actually has negative amplitudes sometimes. This stuff, it whacks it off and makes it look beautiful. So does that answer your question, kind of? Any other questions?
You have answered every question.
What?
You can answer every question.
No, I don't want to answer any more questions. We want to get out here and go eat pizza. Any more questions? Answer is no. Yes, thank you. All right, so next month, January 10th, right here, thanks to Dr. Masood, our savior, who gave us a place to meet. And it's going to be Europa Clipper with Walt Kiefer. So good.
First is in January. What is the date in January?
January 10th.
That should be okay.
Yeah, it's always the second Friday of every month, but I'll send you a list of all the.
Classes don't start until 13.
Okay, well, I'll send you a list just like you asked for.
They won't let us do any reservation before the semester starts.
Oh, so we can just come anyway?
But no, I mean, January is fine.
Okay.
From February, but I will take care of it.
Okay, all right.
We just make it difficult. Nobody, there are not any events on Friday. They just make it difficult.
Well, they got to do that for him. Okay, so Mr. Chris, thank you for being our doorman. Okay, next we're going to do door prizes, and we're going to get out of here. We are way over time today. Door prizes. Look at your tickets. We have some wonderful door prizes tonight. Oh, also, I got this blow up map of the sky. If anybody wants this thing, you can have it, okay? Somebody gave it to me to give to a teacher. I don't know anybody to give it to, but if you guys would like this, you blow it up. It's got all the constellations on it. Go great with your mug, by the way. Right? No. Yeah, did it work? I have one kind of like that somewhere. 626. 626. All right, come on down here. Okay. I have an extra large Eclipse t-shirt. I have an extra large Minions t-shirt. Hold on, don't hang in there. I also have some nice books. I have National Geographic Backyard Guide to the Night Sky. I have an observing log. You can write all your deep thoughts in this observing log. I have a book called White Holes. You liking this stuff?
Nat Geo.
Which one?
The Nat Geo is the first one.
Oh, this one? Thank you. All right. All right. Go. All right. 617. John, get down here, man. Oh, John, you know what? Do you want to write your deep thoughts about what you see in the sky in your astronomer's journal? Yeah. I have the 2024 Night Sky Almanac. I got these t-shirts.
You know, how about the Eclipse t-shirt?
You want the Eclipse t-shirt?
Yeah.
Thank you. All right, great. Go. All right. All right, 615. Come on, Max, get down here. Let's see, Max. I gotta think of something you'd like to have. Max, what would Max like to have? You want a book? 2024 Night Sky. That's actually good. It doesn't change from year to year. So it doesn't matter if it's 2024. It's a good book. I got a journal for you to write your deep thoughts in. Oh, White Holes is kind of a physics book. You like that one, right? You want that one? Which one?
Well, okay.
These are journals. Okay, that's a good one. All right, good. All right. We'll do maybe two more. I don't know how many of these you guys can stand. 624. All right, Mr. Venezuela, right? Come on down here. Okay, I got a Minion t-shirt. Listen, I'm grateful. What, you like this one? What?
Yeah, hold over here. I'll toss it back. I just want to look at it.
All right, that's fine. Do you want it? Okay, got a Minion t-shirt. I've got a journal to write things in. I've got, a night light. Hey, look, a moon and stars night light here. I've got, from Rick, we have some space shuttle crew pictures from different space shuttle missions. I got a package of astronomy postcards. Is it anything doing anything for you?
Yeah.
Which one?
What about? No, I don't have CDs. So,
Oh, you can't do that?
no.
All right. How about something?
Nowadays.
Oh, I've also got a moon map. Hold on. I also got the moon map. There's a map of the moon. Tells you where everything is.
Okay.
You like that? Told you, like 1 out of every 4, David. See, 4, right? Told you. Every 1 out of every 4 is a moon map here. I don't know why.
Thank you.
You're welcome. All right, 631. What's funny about 631?
You missed.
631. Connie. Woohoo! Okay. Would you guys want a Minion t-shirt?
Yes.
Oh my gosh, really?
I am a Minion fan.
There you go, Mike. All right, Minions. Okay, maybe, let's see. All right, maybe one more. 6 2, 1.
Don't tell me, it's me.
Is it you? Come on down here, Dr. Masood. Now I know what you need. Come on. Look, I know what you need. 621. Look, see these astronomer journals? You can write all your deep thoughts in here about your astronomer. You have that?
Do you have a t-shirt?
No, I just gave away all the t-shirts, but I have a night light.
Okay.
Wait. I got one more thing. I have some astronomy socks.
Night.
You want the night light?
Yeah.
Okay.
Thank you.
All right. What?
I made those socks from Starry Night that I got the last year.
Yeah. Oh, yeah. You like them? Excellent. Yes. Okay. I'll tell you what. I'm just going to do one more because I know you guys look really disappointed out there. I saw some really sad faces. What?
It is Christmas.
I know. I could just give away this whole box of stuff. Okay, hold on. Maybe we'll do a couple more. Okay, 637. 637. Do I got a 637? All right, Reed. I know where I need to get Reed. Reed, I've got a ZWO.
GWO
A
keychain.
ZWO keychain.
No,
No, I'm not gonna do it. This Reed actually contributed to this. You got a moon map, right?
I'll take another.
No. You don't want
No,
to.
no,
Do you really want another moon map?
my kids take them, yeah.
Do you really need another one? Okay. Okay, it's 2 out of 4 now.
All right.
All right, Reed. You need to see David. He makes those things for us. Okay, this will be the last one, maybe. 637. 637. I'm seeing people putting coats on. How'd that happen? You can't have 2 door prizes. 630. All right, come on here. Let's see. I've got astronomy postcards. I've got astronomy socks. I've got a map of Saturn. If you ever go to Saturn, you might need a map. I've got a map of Jupiter. I've got a moon map.
Postcards.
You want the postcards?
Yes.
Excellent. There you go.
Thank you.
Oh, you're welcome. All right, very good. Okay, I think that's it. So see you at Mod Pizza. See you next month. Thanks for coming. Oh, gee. God, we're a half hour over. What? Yeah, take it.